Hi everyone, I wanted to go through a couple more examples here of Newman projections and chairs since it's going to be on your first exam. Looking at the top problem here, I'm looking at a molecule that has two carbons connected, and if I think about looking at the projection from this direction, there's my eyelashes, I'm looking down this bond right here, and I want to draw my Newman projection exactly as I'm seeing it. So my hydrogen is sticking up. I'm going to draw it just like that. And again, if you're drawing from this direction, this is going to be on the right side. So so you can sort of imagine, if you're sort of looking down this carbon-carbon bond, if you stick your arm out, your right arm will be where the chlorine is and the bromine will be on the opposite side. So that would be this. And then looking back, I have another carbon behind the one with the hydrogen. And that's eclipsing, so the chlorine would be eclipsing. And then looking down that bond again, I have the bromine eclipsing the chlorine. And I have the hydrogen in the same plane as the bromine. So again, you want to make sure you kind of understand that these things are going to be in the same plane. So the hydrogen and the bromine, these in pink, are in the same plane. This chlorine and this bromine on the right side carbon are in the same plane, and the chlorine and the hydrogen are in the same plane. But remember, you have free rotation around this bond right here. So I can draw this molecule. I can move around my bonds, and then I can redraw my molecule. So let me go ahead and do that. Let me just move everything. I'll keep everything in the front the same, and let me move everything in the back a little bit. Let me draw another Newman projection for that. Kept everything in the front the same. My hydrogen at the top, chlorine and bromine. I didn't move any of those, but I am moving my chlorine a little bit and my bromine a little bit and my hydrogen a little bit. Now if I want to move this again, so that I don't have so much eclipsing, so this would be sort of a gouache, I might want to have my chlorines and my bromines on opposite sides. So let me move my molecule, again. Turn it again, clockwise. Keeping everything in the front the same. Moving the stuff in the back. And the most stable would be with the biggest atoms that are going to be anti to each other. Those would be the bromines. So again, when I told you in class, you want to make sure you just keep the order the same. So if I'm looking at my back molecule or my back atoms right now, and I want to make sure that it goes in a clockwise fashion: bromine, hydrogen, chlorine. And I drew my bromine where I'd want it, so then I have to draw in my bromine, then going clockwise, hydrogen, and then chlorine. And if I wanted to convert this back to a line drawing with dashes and wedges, my hydrogens would be in the same plane up and down, look like that. And my bromines, so these are going to be wedge, and these are going to be dash. I'm going to go ahead and draw those in. So I have the chlorine as a wedge, just like it was in the first drawing. Chlorine as a wedge. I also have bromine as a wedge. And as a dash, I have, in the first carbon, I have a bromine as a dash. And I'd have my chlorine as a dash. All right, so going, I have this bottom molecule and it says draw all the conformations of the following compound. When it says that, what it wants you to do is to move everything 60 degrees. So I'm going to move the first 60 degrees, and I would encourage you to just stay with clockwise. I like to move the back carbon, but you can move the front if you'd like. So I'm moving everything 60 degrees. That means that this hydrogen is going to be eclipsing that one. This hydrogen is going to be here, and the methyl and the iodine are going to be eclipsing each other. This is called eclipsed. And this would be the worst, highest energy conformation because the larger groups, the iodine and the methyl, are eclipsing each other. Now I'm going to rotate again by 60 degrees. Rotation. And again, I'm only changing the location of one set of atoms on the Newman projection. So now my methyl is here. And then I have hydrogens in the other positions. This is a gauche. Then I'm going to rotate again. And now my, again, I'm going to keep the iodine and the hydrogens in the front the same positions. Now my methyl is eclipsing the hydrogen. And I have hydrogens in the other positions. Hydrogen and iodine are eclipsing. I'm going to rotate again. Keep my iodine in the same spot, my hydrogens. Now I have another gauche. And now I'm going to rotate again. Sorry, I'm sort of losing space here. Front atoms stay in the same spots. Back ones move, so now my methyl is eclipsing this hydrogen. And then one more twist would get me back to my starting molecule. So I'm going to give these numbers, and we're going to draw a potential energy diagram. I'm going to call this number 1, number 2, number 3, number 4, number 5, and number 6. I'm going to draw a potential energy diagram here. So I know that number 2 is the absolute worst. Number 1 is the gauche, where the iodine, so the iodine and the methyl are kind of close to each other. I have that gauche with the iodine and the methyl close to each other in 2 scenarios here. And then I have the methyl and the iodine as far away from each other as possible. So, oops, I forgot to name these. Over here, this is going to be our anti, where the bigger groups are opposite each other. So this is the best, lowest energy scenario. So the first one is a gauche, and I know that this one, this is going to be, let me just write a couple of notes here. This is going to be the highest energy. This is going to be the lowest And this is going to be low, mid. I'm going to call this low, mid. So let me just kind of say, okay, maybe this is number 2. All right. So if this is my potential energy diagram, I'm just sort of estimating here energies. So in number 1, this would be number 1, this is number 2, this is number 3, this is number 4, this is number 5, this is number 6, and this is number, back to number 1. Notice number 1 and 3 are the same energy, so let's sort of connect these in a potential energy diagram. And again, the highest energy is when you have the larger groups, larger atomic number, larger atomic mass, eclipsing each other, and the lowest is where those larger groups would be anti to one another or opposite one another on the potential energy diagram. All right, let's again draw a Newman projection. So I'm going to draw the Newman projection from the wedge and the dash. So for this particular example, it's important that you follow directions when you're drawing your Newman projections and looking at where the eyes are. So for this one, if I imagine I'm looking at the molecule from this direction, my hydrogen is facing the left, and what's going down is this group. So this is a propyl. I'm just going to abbreviate this as PR for propyl. The hydrogen is facing the left, and I have a methyl that is going out to the right. Then behind that, going up, I have a methyl, and in the same plane as the hydrogen, I have an isopropyl, IPR. This is IPR, isopropyl. And then this D right here, this is deuterium. Deuterium. So this is a hydrogen atom with 1 neutron. The most common isotope of hydrogen has 0 neutrons. That's why we call it usually just a proton. But deuterium has 1 neutron. So that is a deuterium, and that is going to be in the same plane as my methyl. So that is how I would draw that. Again, you can rotate your molecule. So let me rotate the back to get the propyls and the isopropyls to be anti one another, and then we can redraw it. There, I have the isopropyls that are opposite one another. And then let me just go ahead and draw that. And so you can draw these molecules from different angles, but I'm going to keep it the same as I started with. So there is the propyl, and my hydrogen is coming out of the plane of the board. The methyl is going into the plane of the board. That's this front carbon right here. Let me circle that in pink. That's this carbon right here. This carbon is attached to a carbon behind it, and in this case, I'm going to have the isopropyl going up, and then going down is going to be the hydrogen is going to be the wedge. Oops, the deuterium is going to be the wedge, and the methyl is going to be the dash. The methyl is going to be the dash. And again, these are in the same plane. You can go back and check that. And these are in the same plane, the hydrogen and deuterium. What I mean by same plane is they should both either be dash or wedge according to my Newman projection here. So that drawing equals that line bond drawing. All right, now we are going to draw the Newman projection from this other angle. So what I see is facing down is the OH. Going to the right is an ethyl. This is ethyl, ET. And then this is actually a sec-butyl, but I'm going to draw that in because I told you guys you didn't have to have that memorized. So there we go. And then looking down that bond, what I see sort of eclipsing the OH there is this group. So I'm going to draw that. And then in the plane of the ethyl, there is a hydrogen. And in the plane of the of the sec-butyl, there is also this ethyl, methyl. So that one will look like this. And again, I could rotate this around. Let me rotate it. Not messing with the front carbon again. I want to rotate this so my bigger groups are opposite one another. So I rotated this all the way over here, and I just want to make sure I maintain the order on my back atoms. It goes this big group, then ethyl, then hydrogen, going clockwise. There we go. And I could redraw that. It would look like this. And then my ethyl would be here. Ethyl. And my sec-butyl would be there. And then on the back one, I want to make sure I draw my ethyl and the other group in the same plane. And then I have on the back carbon the ethyl and the sec-butyl in the same plane. So again, lots of ways to draw the molecules. If I had this one right here and I was just converting this back into a line bond, what I would do is I usually start from the left. So I would draw from the left like that. I always start with just a zigzag. This tert-butyl is going to be up. And then what's on the right? On the right or facing out wedge is going to be a methyl. So again, these are in the same plane. And these are in the same plane. So I have that methyl group. And then on the wedge, sorry, on the dash, I have that ethyl. Then on the behind carbon, facing down, I have another cycbutyl right there. And then my wedge is going to be an ethyl. And my dash is going to be a methyl. So there I converted a Newman to a line bond drawing. Down here, identify whether each pair of compounds are constitutional isomers, stereoisomers, or identical. For this one, I'm going to highlight, I'm going to tell you these are identical. I'm going to show you where they're identical. You can see that if I call this number 1, 2, and 3, and this is number 1, 2, and 3, I have a methyl on carbon number 2 in both scenarios, and I have an ethyl on carbon number 3 in both scenarios. These are the same. Okay, on the down one, what I'm looking at here is I have a trans molecule. So if this, let's say this is carbon number, let's call this carbon number 1, 2, 3, and 4. At carbon number 1, I have a methyl that's facing down. Okay, that's correct. So 1, 2, 3, and 4. But at carbon number 4, this is an isopropyl. So this is an isopropyl that's facing up. And in the chair at carbon number 4, I have an isopropyl that's facing down. So on this side, I have an up, I have a down methyl, up isopropyl, and on the right side, I have a down methyl and a down isopropyl. That makes these stereoisomers. The left one with down and up, this would be trans. And the right one where it's down, down, that would be cis. So those are stereoisomers. In C, I have a methyl attached to carbon number 1 and 3. And the other one, I have carbon number 1 and 2. I have the same number of carbon atoms, I have the same number of hydrogens, so they're not different molecules, but I have the methyls attached to different carbons, so these are constitutional isomers. Down here it says, draw both chair conformations of the molecules below and determine which one is more favorable. So again, I'm just sort of going to start numbering in a clockwise fashion. And it's a bit arbitrary. I'm going to do the same thing at the bottom. Draw my chairs in. All right, there's another set of chairs. And then I'm going to go ahead and number my carbon atoms. I always call the one facing down number 1, 2, 3, and I only need to go up to 4 for the top one. 1, 2, 3, and 4. Again, note that when my chair is sort of this little angle right here is facing down. Right there, when that's facing down, that's where I start my carbon number 1. When that angle is facing up, that's where I start my carbon number 1. Didn't mean to erase that entire thing, but let me fill it back in. Oops, black. Okay, not the neatest chairs, but it will do. So on carbon number 1, I have a chlorine, and again, that dash means down. So dashes mean down, wedges mean up. It needs to be facing direction up. It doesn't mean equatorial axial. It means up or down. So my chlorine on carbon number 1 is facing up. That means it's going to be equatorial. At carbon number, oops, I'm sorry, I did that totally wrong. I'm following my own directions. Chlorine facing down, that means it's going to be axial. At carbon number 2, I have a methyl group, that's going to be facing down. That's going to make that equatorial. And then I don't have anything at carbon number 3. At carbon number 4, I have an isopropyl, that should be facing up, which means that's axial. Now, when I do the ring flip, everything that's equatorial is going to be axial, but I'm going to keep the same direction. So when I move my chlorine to the other chair, it also needs to stay facing down. But now it's going to be equatorial. So notice, chlorine went from axial to equatorial. And then everything else that's equatorial is going to be axial and vice versa. So my methyl on carbon number 2 was equatorial, and now it's going to be axial. Carbon number 3, I have nothing. And then at carbon number 4, I had an isopropyl that was axial. And now at carbon number 4, it's going to be facing direction up, but it's going to be equatorial. Question is, which one is more favorable? Now this is kind of a judgment call. So I have a methyl group that's facing down and it's going to be axial or equatorial, but I have these bigger groups. So my isopropyl is going to be the biggest group here, and I have a chlorine. Those are both going to be axial or equatorial. I would say that in the right molecule, because I can get those bigger groups to be equatorial, overall, the right molecule would be more favorable. Alrighty, let's draw in the substituents for B on the chair. Now I'm going to put my numbering in my chair, just like I did before. And I'm going to add my substituents. So at carbon number 1, I have an ethyl and it's facing direction up. That means it's going to be equatorial. At carbon number 2, I have a methyl that's facing down. That's going to make that equatorial. At carbon number 5, I need something to be facing up. It's my methyl facing direction up. I can already tell this is going to be the more favorable one because everything that is equatorial. And then in the right chair, everything's going to end up being axial. So at carbon number 1, I need that ethyl to be facing up, which means it must be axial. At carbon number 2, that methyl needs to be facing down, so that's going to be axial. And then at carbon number 5, my methyl that was equatorial is now going to be axial. So I can tell that for sure the one on the left is going to be favored. And I hope this was helpful for you guys.